So welcome guys to our another new section, Reciprocating Air Compressor Part 6. Today we will be discussing about multi-stage compression. Let me first explain what are the drawbacks of single-stage reciprocating air compressor for producing high pressure. Let's say if you need to produce very high pressure, say about 10 bar, and if you are performing that process with the help of a single stage compressor, then the following drawbacks will occur. First one is large cylinder size. Since the pressure is higher, the pressure which we need to produce is higher, and in single stage reciprocating air compressor, as you all know, the compression takes place due to the reciprocating motion of the piston. So in order to produce high pressure, the cylinder size must be larger. The second one is, you know that during compression the temperature and pressure both increases. The temperature and pressure both increases during compression. The high temperature which is produced as a result of high pressure causes many problems, and practically it is very difficult to remove this high heat during the combustion process. And the third disadvantage is, since the pressure we need to produce is much higher, we require heavier working parts. It will create problem. It will create the balancing problem of the compressor. One of the after effects of this balancing problem is the torque encountered in the compression is not uniform. Rather, it is fluctuating. Since the torque which is produced is fluctuating, we require heavier flywheel, so it will create a problem. And you know that as a result of compression, both temperature and pressure increases. This high temperature which is produced can burn the cylinder head, and it can even burn the lubricating oil also. So these are some of the drawbacks which are commonly encountered during the compression of very high pressure with the help of a single stage reciprocating air compressor. One method to rectify this drawback is compressing the air in one or two small compressors with an intercooler in between them. That is called multi-stage compression. The figure shows a two-stage reciprocating air compressor which is connected with the help of an intercooler. This is the low pressure cylinder, that is the low pressure compressor, and this is the the high pressure compressor. The air is drawn into the low pressure compressor during its suction stroke, and after compression it is compressed to very high temperature and pressure, as you all know. It is drawn into the intercooler, where the temperature is lowered, the pressure remains constant. That is, constant pressure cooling takes place in the intercooler. After that, it is drawn into the high pressure compressor, where it undergoes compression again, and we get high pressure, high temperature air from the outlet of this high pressure compressor. This is known as two-stage reciprocating air compressor with an intercooler. This is the schematic representation of a two-stage reciprocating air compressor. Here P1 T1 represents the state of the air which is entering the low pressure compressor, and P2 T2 represents the state of the air which is leaving the low pressure compressor. And you can see that in intercooler constant pressure cooling takes place. That is, the pressure P2 remains the same, the temperature is different. The temperature T3 is lower than temperature T2. And then it enters into the high pressure cylinder, and after that after compression, the pressure increases from P2 to P3 and the temperature increases from T3 to T4. This is what happening in a single stage reciprocating air compressor with the help of an intercooler. The figure shows the PV diagram for a two-stage reciprocating air compressor. You know that in PV diagram, the volume is plotted along x-axis and the pressure is plotted along y-axis. The dotted curve represents the isothermal compression and the other curve represents polytropic compression. We can see the curve 1, 2 represents the compression in low pressure cylinder. Represents the compression in low pressure cylinder. And 2, 3 represents the constant pressure cooling. 2, 3 represents the constant pressure cooling which is taking place in intercooler. And 3, 4 represents the compression which is taking place in the high pressure compressor. So as a result of two-stage compression, the pressure which is entering the low pressure compressor at state 1 is compressed to pressure P4. Here P2 and P3 both are same. And you know that the work done for isothermal compression is lower when it compared to polytropic compression. That's why the dotted curve represents the isothermal compression and the other curve represents the polytropic compression. So 1, 2 represents the compression in the low pressure compressor and 2 to 3 represents the cooling in the intercooler and 3 to 4 represents the compression in the high pressure cylinder. Now, this shows the same PV diagram. Here 1 to 2 the compression in low pressure cylinder and 2 to 3 the intercooling and 3 to 4 the high pressure compression. Let's imagine here this curve represents the polytropic compression and this dotted curve represents the inner dotted curve represents the isothermal compression and the outer dotted curve represents the isentropic compression. Let's focus on the polytropic compression. Let's imagine if the compression is done by using a single stage compression without clearance volume. Then what will happen? The curve, the PV diagram will start from here, it will end at here, then it goes to 5, then it ends at here. So if the compression is done without two-stage compression or if the compression is done in a single stage, then the curve will start from here, ends at here, then it goes to 5, then finally it ends at here. So due to this two-stage compression, the curve now becomes 1, 2, 3, 4 and finally it ends at the point 3. So now it's clear. You know that the area under PV diagram represents work done. This area is larger as compared to this area, right? So we can say that if we employ a two-stage compression with intercooler, the power required to drive the compressor is much lower because the work required for a two-stage compression is much lower as compared to that of a single-stage compression. Clear? So the work required for a two-stage compression is much lower as compared to a single-stage compression. So these are some of the advantages of multi-stage compression. As explained in the previous slide, the work done per kilogram of air is reduced in multi-stage compression. The second point, high volumetric efficiency. In the previous lecture, that is about volumetric efficiency, I clearly explained that if the temperature of the air which is entering into the compressor, if it is get heated when it comes in contact with the cylinder walls, it will decrease the volumetric efficiency. That is, the volumetric efficiency of the compressor will decrease as the temperature of the air gets heated or increases when it comes contact with the hot cylinder walls. Here there is no such problems because intercooling improves and there will not be such temperature rises. So, as a result of multi-stage compression, the volumetric efficiency of the compressor increases. That is, high volumetric efficiency is one of the greatest advantages of multi-stage compression. Then, since the parts are much not lighter, the mechanical balancing will not be a great problem. Then it reduces the leakage losses, and since there is no chance of getting the lubricants burned, it can provide effective lubrication. Since there is not there is not such problem like balancing, more uniform torque will be produced. Since the balance is better, the torque will always be uniform. So these are the some of the advantages of multi-stage compression over single-stage compression. The work done kilogram of air is reduced, high volumetric efficiency, better mechanical balance, reduces the leakage loss, effective lubrication, more uniform torque. Now, there are two types of intercooling which is encountered in two-stage reciprocating air compressor. The first one is perfect intercooling or complete intercooling. The second one is imperfect intercooling or incomplete intercooling. If the temperature at the outlet of the intercooler is equal to the temperature at inlet of the low pressure compressor, then that type of cooling we call it as perfect intercooling. The temperature at the outlet of the intercooler must be equal to the temperature at the inlet of the low pressure cylinder, then that type of cooling we call it as perfect intercooling. If the temperature is not equal, then it is known as imperfect or incomplete intercooling. It will be always greater than T1. So intercooling are of two types, perfect intercooling and imperfect intercooling. Now, you know the formula for calculating the work done of these low pressure compressors. Since you know the inlet condition P1 T1, the outlet condition P2 T2, you know the formula for calculating the work done of the low pressure compressor. N divided by N minus 1 into P1 V1 into P2 divided by P1 the whole raised to N minus 1 minus 1. And now you know the formula for calculating the high pressure work for the high pressure cylinder. That is N divided by N minus 1 P2 V2 into P3 divided by P1 in the whole raised to N minus 1 minus 1. Here P2 P1 represents what? The pressure at outlet and the pressure at inlet. In this case, the pressure at outlet is P3 and the pressure at inlet is P2. So that's why P3 and P2 comes here. So the net or the total work will be what? This algebraic sum of the low pressure compressor and the high pressure compressor. These equations we already derived in our lecture 1. So, if it is perfect intercooling, you know the condition T3 is equal to T1. And you know the ideal gas equation. For a perfect gas, you know the formula P1 V1 is equal to MR T1. R is nothing but the characteristic gas constant. So here the pressure is P1, the volume is P1 and the temperature is T1. When you apply here P1 V1 is equal to MR T1. Here the pressure is P2, the volume is V2 but the temperature is T3. When you apply here, when you consider the state here, then you have P2 V2 is equal to MR T3. You can see for perfect intercooling you can see T3 is equal to T1. Since M and R are constant and T1 is equal to T3 for perfect intercooling, you can say that P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. So, you know the formula for calculating the low pressure compressor. You know the formula for calculating the work of the high pressure compressor. You also know that the net work will be the algebraic sum of these two quantities. Then, in case of perfect intercooling, you also know that P1 V1 is equal to P2 V2. So, apply or replace this P2 V2 with P1 V1 in case of perfect intercooling. Then the formula becomes N divided by N minus 1 common. P1 V1, now after replacing it, now it will become common. So P1 V1 into then this term minus 1 minus 1, it will become minus 2. So this is a formula for calculating the work done for a two-stage reciprocating air compressor with perfect intercooling. In case of imperfect intercooling, just add these quantities. So the economical value for pressure ratio per stage is between 3 to 5. If the pressure ratio, that is the outlet pressure by the inlet pressure, is between 3 to 5, the compressor will be more economical. And these are some of the values for the maximum discharge pressure. If it is a single stage compressor, the maximum discharge pressure must be 5.5 bar. If it is a two-stage compressor, the maximum pressure will be 3.5 to 21. And if it is three-stage, the maximum pressure will be 21 to 70 bar, in between 21 to 70 bar. So, in this lecture, we learned about what do you mean by multi-stage compression, what are the advantages of multi-stage compression, what are the drawbacks of single-stage compression. Then we know, when we explain the working of two-stage reciprocating air compressor, you know the formula for calculating the work done for a two-stage reciprocating air compressor, because there are two cylinders. You know the formula for calculating work of each cylinders. Then the two concepts, perfect intercooling and imperfect intercooling. Then the work done for a two-stage reciprocating air compressor with perfect intercooling. So in the upcoming videos, we will be deriving the formula for calculating the minimum work in case of two-stage reciprocating air compressor with perfect intercooling. So thank you.